Hello, experts. It's a great honor to be nominated for International Research Awards on New Science Inventions under the category of Best Research Award. My name is Huang Renkai. I'm a teacher in the School of Mechanical and Electrical Engineering of Jiangxi University of Science and Technology. The topic of the report is grade 3 composite support structures for lattice parts in selective laser melting. As we all know, the functions of the support structure mainly include the following three: A. Anchors for initially floating objects. B. Melt, pour heat dissipation. C. Thermal warping prevention. A support structure is an essential part in a selective laser melting processes. It is required especially in cases where heat accumulates in overhangs. Heat stress and warping may occur due to the heat accumulation in overhangs. These defects ultimately affect the dimensional and geometric accuracy of a part. The two figures shows the support structure generation for sleeve lattice part, whose lattice structure need or doesn't need the support structure using Magic's software respectively. Like this one, this orientation of the sleeve lattice part. This orientation for the SLM printing, the lattice structure need to add a support structure, but this orientation of the part is not need to add support structure. For example, for situations where the lattice structure doesn't need the support structure, Magic's software generates the support structure for 5,000 overhangs of sleeve lattice parts, which leads to redundant support structure and need to be removed manually. Therefore, a new approach is urgently needed to improve the efficiency of the support structure generation. Although scholars have proposed various support structure generation methods, few scholars consider support structure generation for lattice parts. The traditional support structure generation method has the problem of support redundancy, especially when the forming object is a lattice part. As a result, the lattice structure interferes with the support structure, and even if it can be formed smoothly, the support is difficult to remove. Therefore, it is essential to develop a support structure generation technology for lattice parts. Fig 1 shows the workflow of support structure generation for lattice parts. First, we use a multi-criteria genetic algorithm proposed by Huang et al. To obtain a Pareto optimal set of the lattice part build orientation. Then choose a build orientation in the optimal solution set according to the user requirements. For example, in Fig 1, the build orientation corresponding to the frame's minimal adaptive feature roughness is chosen. Moreover, the point overhang of the lattice structure is identified based on its skeleton. Finally, the grid tree composite structure is generated to support the frame and the lattice structure. The generation workflow of grid tree composite support structure for a part is shown in Fig 4. First, identify the area to be supported, which includes point overhang, face overhang, and edge overhang, as shown in Fig 4a. Then use the raster sampling method to obtain the support points and generate the backbone of the support structure, as shown in Fig 4b. Next, use the sweep algorithm to generate the grid structure, as shown in Fig 4c. Finally, add branch structure based on the grid structures to obtain grid tree composite support structure, as shown in Fig 4d. Step 1. Support points grouping. We group the support points so that the backbones of support structures are connected only in the group to improve the ease of removal of the support structure. Fig 5 shows the grouping method. The effective support point group includes at least one support point and a maximum of 6 support points. The grid structure is only generated between adjacent support point in the group, leaving gaps between groups. Fig 6 shows the process of the establishment of support then pairs, and Fig 7 shows the schematic diagram of sweeping to generate a grid structure. And Fig 8 shows the schematic diagram of branch contact point generation. Fig 9 shows the schematic diagram of tree shift structure generation. And the Fig 11 shows the support structure generation for lattice parts. Firstly, the projection of the frame's area to be supported on the XOY plane. Then, sampling of support points of solid parts. Then, support points not included in the framed area to be supported. Finally, grid tree composite support structure generation. The generating results of the grid tree composite support structure for the sleeve and bracket lattice parts are shown in Fig 14 and Fig 15. Fig 14 shows the support generation results when the part build orientation is the corresponding orientation of the solution 1 of the sleeve lattice part. Currently, the lattice structure has no point overhang, so only the support structure needs to be generated for the frame's overhang area. Fig 15 illustrates the support generation results for the two lattice parts in the build orientation with points overhang, like this. Those lattice structure all need to added support structures like this, this and this. And Fig 16 shows images of printing the lattice part by SLM. A2E is the sleeve lattice part, and F2J is the bracket lattice part. We can see that the fabrications were all successful. We conducted the SLM printing experiment using a cantilever lattice model like this. A cantilever lattice model. To further investigate the effects of the support generation by matrix RP and all method on printability. To make the comparison a fair one, we used the same face overhang and point overhang as in our experiment. Fig 17 A to C are three support structures designed by experienced technologists using matrix RP software. Fig 17D is the support structure designed by our approach. Note that the model supported by tree-shaped support structure has obvious one-page deformation. One-page deformation, like we can see the Fig 17A, and the model supported by block support structure has massive residual support after the support removal. Like we can see Figure 17B, the supported model generated by matrix RP of adding solid and block supports and all methods performed well in terms of forming quality of overhangs and lattice structure. We can see Fig 17C and D. we measured the 3D dimensions of the SLM printed models to evaluate the effect of the grid tree composite supports generated by our approach on the forming quality of the SLM printing models. Table 3 lists the dimensional deviation and warpage of the SLM printed model. We can see that 1. Using grid tree composite support generated by our approach and solid and block support generated by matrix RP can lead to less warpage of the cantilever model compared with the other two supports generated by matrix RP. 2. There is no significant difference between our method and the 3 methods of matrix RP in the dimensional deviation of the SLM printed model in the y-axis direction. The table 4 shows that the amount of support material our approach saves is about 72.63% on average. This article proposed a grid tree composite support structure to solve the problem of generating support structures for lattice parts. The major findings can be summarized as follows. The support structure is generated to support the lattice parts overhang area, including the frame's overhang and the points overhang of lattice structure. The feasibility of our method is verified by generating the grid tree composite support structure for 2 test lattice parts and its SLM printing results. Compared with the 3 support generated by matrix RP, the grid tree composite support proposed by the article result in less support volume with a small amount of warping deformation. Meanwhile, the removability also can be guaranteed. That's all. Thank you. Thank you very much.